how do we actually create some stability in this type of a parasite-host model? The first thing that should come to your mind is that that initial model made some very simplifying assumptions. It made assumptions about how these parasitoids search. It made assumptions about how the population growth of the hosts actually occurs. There's basically no density dependence in those populations, and so on. And so one of the ways in which we can explore whether the interactions between parasites and hosts could be stabilized is by altering some of these particular assumptions in the models to see if it would actually create this stability that we know exists in some systems. So how do we actually do this? What some researchers have tried to do is to include some features about how the parasitoids actually search for their prey, relaxing this assumption that their search efficiency is constant throughout their lives or is constant across the density of the host. And one observation that was made by researchers early on is that as the parasitoid density actually increases, there's no reason to think that their efficiency of searching for hosts will remain constant. In fact, the parasitoids might actually be interfering with each other. Maybe they're spending more time trying to get on top of a host and bumping each other off than when the densities are low. And therefore, the searching efficiency and ability to overcome these negative interactions is going to decrease their ability to successfully parasitize hosts. So you could think of this searching efficiency as not just how good are they at searching for the host, but what results in a successful attack at the end. And so there's various empirical studies that have actually shown that these relationships are often negative. That as parasitoid density increases, that ability to actually successfully parasitize the host actually goes down. So one way you can model that is you can see that these are lines. These lines have a particular slope right here, and rather than assuming that the searching efficiency is constant, you can actually have it change as a function of density. You can have it be this negative relationship as a function of density. Don't worry about how this actually comes about, but it's basically this relationship here put into this form. So what happens when you actually include some kind of feature that changes the searching efficiency of the parasitoid? Well, this is just a series of simulation models. This is the Nicholson Bailey model in its traditional form, where you see these ever-increasing oscillations of predator and prey, or parasite and host. The host is the red line. The parasitoid is the blue line. The host goes to extinction because this is the unstable nature of those Nicholson-Bailey dynamics, which then creates no hosts available, and the parasitoid goes to extinction. This is under the assumption of no interference between parasitoids as they're searching. As you increase the disturbance or the effect that parasitoids have on each other, you can see that the oscillations become a little less extreme in this case here, and the oscillations kind of continue for a longer period before they go extinct. And when this interference is actually quite high, you actually can get stabilization of this interaction so that the parasitoid doesn't make the host actually go extinct in this case. So what this is basically doing is allowing the hosts to get away more because the parasitoids are duking it out or otherwise interfering with each other. And when that happens, there's enough hosts the next generation to be utilized by the parasitoids. So that's one way in which people have suggested that stabilization of parasite-host interactions might actually occur. Another possibility is that there are ways in which these hosts might actually escape parasitism in the first place. So one way is for parasites to kind of be so distracted by each other that some of the hosts might get away. Another is that there might actually be refuges in the environment that allow some fraction of hosts to actually not become parasitized. And there's some others that we're going to talk about as well. So, for example, there could be some size classes or stage structure of an organism that simply can't be utilized by a predator or a parasitoid. So that there could be an escape in time that allows these host populations to not be overexploited by their parasitoids. And if that happens, again, some fraction of the hosts are going to escape to the next generation, which then allows the population not to go extinct and to allow the parasitoids to be also maintained. So this is kind of a size or a temporal refuge. The last one I want to talk about here is that there could be an escape in space. This gives rise to this idea of metapopulations. That is, that rather than thinking of the population as a closed entity where all of the interactions play out within that local area, that actually what you have is a series of smaller linked populations, and they're linked by dispersal, emigration, and immigration. This is one of the fundamental assumptions that we actually started with both the Locke-Volterra and the Nicholson Bailey models, is that these populations are closed. Well, when they're closed with these very strong effects of predators on or parasites on the host population, this creates an unstable this creates some conditions that result in unstable population dynamics. So having refuges in space that have not yet been discovered by a natural enemy is one way in which these populations can persist for longer periods of time. So another way to say this is that it's possible that locally predator-prey or parasite-host populations are not necessarily stable. They might actually go extinct locally, but at a global scale, when you actually look at the ensemble of a series of metapopulations linked by dispersal, that at that broader ensemble, there is always some population that has not gone extinct because the predators haven't been able to find it yet. And that these subpopulations fluctuate out of phase with each other so that populations that are declining can basically be rescued by immigrants that come in and contribute to the population. The classic example of this actually comes from some studies done by Carl Huffaker back in the 1950s. Now, Huffaker was studying spider mites. Yes, you guessed right, the nemesis that I had working in California agriculture. And what he was interested in was whether the interactions between the six-spotted spider mite, this is different than the interactions that he was studying were between the six-spotted mites, slightly different than the spider mites that I was interested in, and their predators, these guys here, could be maintained by metapopulation types of dynamics. And what he did is he set up a series of small little habitats. These little oranges here and these oranges were shielded so that the mites could only feed on this top part. This just made it easier for him to count the mites, but in reality, in the real world, they would be feeding on this whole thing. And then he put these oranges here with the mites on them in an arena that had different densities of oranges with mites, and then a bunch of areas here that had no mites on them. These are kind of blank oranges you could think of. And the mites could actually kind of crawl down, walk to another of these oranges, and then colonize an orange that had no mites on it before. And he was able to make the passage between one orange and the next more or less complicated by putting down Vaseline and creating little barriers that the mites couldn't actually overcome. And what he found was when you released predatory mites and spider mites and the six-spotted mites on these oranges, that he was able to actually get much longer term persistence here of the predators and the prey when he had a metapopulation, this group here, as opposed to the dynamics that were happening within any one orange. And you can see this kind of illustrated by the fact that populations in this system here actually do go extinct. These oranges here that are red used to have mites on them, the prey mites on them in this time step, and around over here, they don't have them anymore. They've gone extinct. But then there are oranges here that have become colonized that actually have mites on them that didn't have them before. So you could think of this as kind of a cat and mouse game between predator and prey, with the prey constantly trying to find places in this environment that have not yet been discovered by the predators, and the predators always looking around for new sources of prey to consume. And the more complex this habitat is, and it also depends on how good the predator and the prey are at finding these new habitats, the longer these populations could actually be maintained in the system. Again, the stability of the system is not driven by the dynamics within any one little subhabitat here, but is driven by the dispersal and colonization of empty habitats that allows for spatial refuges in these particular systems. Here's another example looking at a parasitoid here, this little pteromalid wasp that is a parasitoid of the larvae of these little bruchid beetles. If you allow these bruchids to exist alone, they have these relatively high populations over time. As soon as you introduce the parasitoid is really good, and they can send the population to zero very quickly. The dotted line is the parasitoid here. And this is what happens when you add more and more units to this particular system. They actually had little dishes with seeds in them that these bruchids feed on, and the seeds and these dishes were either connected to 4 other cells or 49 other cells. And the more cells you have, the longer this cycle can actually maintain itself. Here it kind of died out at 20 generations, 20 weeks. Here it lasted all the way to the 30-week mark. And as you get into a much more complex situation, you can actually see the persistence going out even to 35 weeks and so before things actually went extinct. And again, this is a very controlled situation. It was just an experiment, but it goes to illustrate that the dynamics of these populations might be stable, but due to immigration and emigration out of the system and colonization, rather than there's something inherent about the cycling of the population that actually maintains them.